Okay, let's take a look at example 1 in section 5.7. If you haven't read the material in the book, please pause the video and read the material. But at this point, we want to prove that there's a formula that exists to define the sequence that is right now defined recursively. We want to find what that explicit formula is going to be like. And so the best way to do this is to use iteration, which means just write out a few of the terms and try to see if there's a pattern. So like for example, in this problem, a0 is equal to 1. So when k is 0, I get basically 1. What about when k is 1? So using the formula, I get a1 is equal to a0, because 1 minus 1, plus 2, which is going to be 1 plus 2. So far that's going to be 3. Perfect. So we have 1, 3 so far. What about when k is 2? When k is 2, we get a2 equals to a2 minus 1, which is 1 plus 2. And that's going to be 3 plus 2, which is going to be 5. All right, and let's do one more, and I think you will notice the pattern. So when k is 3, we get a3, which is going to be a3 minus 1, which is a2 plus 2. And that's going to be the previous guy, 5 plus 2, which is now going to be 7. So it seems like we're getting odd numbers always. So it seems like we have 1, 3, 5, 7. So in general, my guess is this. My guess is that if I wanted the kth term, let's say, then I'm gonna have to basically to go from 3 to 7 or 2 to 5 or 1 to 3, I'm gonna have to take the index that I started with, k, and multiply it by 2 and then add 1. So we can test it out. When you put a 3 into this formula, you get 6 plus 1, which is 7. Perfect. When you put 2 into the formula, 2 times 2 is going to be 4, plus 1 is going to be 5, so that's perfect. So this is now an educated guess, and we have to prove this by using some sort of induction at this point. So I'm going to keep that so that you can see where I got my inspiration from, but I feel like this formula works for pretty much anything that's greater than or equal to 1 possibly. Okay, it actually works for 0. a0 is going to be 1, so it works either way. So anyway, we're going to have to prove this by induction. So let's do the proof here. So proof by induction. So let n be greater than or equal to 0, and so the base case is going to be when n itself is equal to 0. So when n itself is equal to 0, what do I get? I get that first of all, the a0 was given to me as a 1, and using the formula, if I guess 2 times 0 plus 1, it's gonna be equal to 1 at the end. So it seems like my formula, which is saying an should be equal to 2n plus 1, it seems like my formula is actually going to work. So this is gonna be true at this point, so that's great. So true. And what about the inductive hypothesis? So in the inductive hypothesis, we will suppose that our formula works for some random integer, and we want to show that it's true for the next integer. So in other terms, I want to show that an plus 1 is equal to 2n plus 3. And the way I'm going to do that is by using my recursive formula. First of all, so I know that from the start of the problem, I know that ak is equal to ak minus 1 plus 2 in general. So that tells me that if I put an plus 1 into the formula, I should get basically a sub index n plus 1 minus 1 plus 2, which is the same thing as saying an plus 2. But what do I know about an? Well, according to what our assumption is, an is supposed to be 2n plus 1. So let's go ahead and make the substitution. So far, an plus 1, then an plus 1 is going to be equal to the 2n plus 1 because of the assumption from the inductive hypothesis, plus the extra 2 off to the side. And that's going to be 2n plus 3. And that's exactly what we wanted, right? That's exactly our goal. So at this point, we are basically finished. So, instead of using this recurrence relation to define the series, we can now use the explicit formula. So the formula that we are guessing is basically the following formula. We are guessing that the ak should be 2k plus 1, where k is some random number that's greater than or equal to 0. So this is another way of redefining that sequence that we have in this problem.